Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today in this tutorial I am going to explain a very new paper called VoiceID Loss, Speech Enhancement for Speaker Verification. This paper came out yesterday. It's a very new paper. This paper is coming from MIT CCL lab. So the authors are Suwon Shon, Hao Tang and James Glass. James Glass is a very well known speech scientist. He is working in CCL lab, is in MIT. He has published a lot of research papers on speech, and Suwon Shon is also one of the PhD student of James Glass. He's done a very good amount of work in dialect identification and so on. And in this tutorial I am going to explain the overview of this paper, and we'll use I'll explain the contribution of this paper is on this line. It's called VoiceID loss. So VoiceID loss is a sort of new type of loss they are using for speech enhancement basically. We'll see what is the exact use case coming slides, and we'll see the experiments and results. So this VoiceID loss is basically invented for improving the robustness of speaker verification. So you might be knowing about speaker verification, also known as SV. Speaker verification is about given audio of someone. You want to know whether this audio is from the same speaker or is the audio from is the speaker who is spoken is the speaker is of interest or any other speaker. Sort of you can think of it as let's say you are speaking to Google. When you say okay Google will know whether you spoke or someone else spoke. It's just about verifying your device, right? That's the idea, just like face verification. So ways you can ask, like if you are interested in speaker verification, what does it has to do with speech enhancement? So this paper is about some sort of combination of speech enhancement and speaker verification. So the idea is usually when we are doing speaker verification, there will be a lot of noises in the audio. Like for example, let's say you are doing speaker verification in some environment where there is a lot of crowd and a lot of background music and all. So that type of situation, you might need to employ one speech enhancement module, which will give you audio which is like clean, and then you can do speaker verification. That is one way of doing it. Just cascade of let's say speech enhancement and speaker verification model. That is one way. But what these cases are saying is, let's say we have a model which does speaker verification, and we use that model to train another model in joint with this model to enhance the speech and does speaker verification. It's sort of, you can think of it as it's a sort of joint training of speech enhancement and speaker verification. We'll see the exact architecture and remaining the other things in the coming slides. But just assume this VoiceID loss is basically some sort of loss which is introduced for speech enhancement to improve the robustness of our speaker verification module. And usually when we train speaker verification or speech enhancement model, we use L2 loss, which is basically reconstruction loss. You can think of as mean square error loss, MSE loss, between clean spectrogram and the spectrogram generated by the model, and we measure that loss. It's also known as L2 loss, and in this case we use something called VoiceID loss. We'll also compare this model with L2 loss baselines. I mean, basically we'll see some other model which actually does use L2 loss, but assume this VoiceID loss is used for speaker verification in this paper, but this can be another baselines models, right? So this is the VoiceID loss. So as I said, to train a speech enhancement model, they use VoiceID loss. We'll see what is VoiceID loss in a coming slide instead of reconstruction loss, right? And usually what happens is when you are generating when you are doing speech enhancement, you don't directly output the spectrogram directly. You actually generate something called masks, binary mask sometimes. So those masks are basically pointwise multiplied with the original spectrogram which basically the mask will be sort of a binary mask, assume a binary mask 0 1 0 1 something like that. When you put it on top of a original spectrogram, wherever there is 0, that bin, the frequency bin, gets suppressed and remaining will be retained, and that people show with that you can get a nice enhanced audio. So we will see all the architecture details in coming slide, and this model also actually performs consistently better than the baselines in case of noisy and even in both clean conditions. That is the overview, and let's see the actual algorithm, actual proposed approach in this paper. So usually when you have a speech enhancement problem, this is speech enhancement problem. Speech enhancement people train the model this way. Assume you have a speech enhancement module, can be a neural network. Yes, let's assume it's a convolution neural network, and this neural network takes in a noisy spectrogram. This is the noisy spectrogram, and this is obtained by some noisy signal. This noisy spectrogram basically goes through this speech enhancement model. Out comes enhanced spectrogram. This enhanced spectrogram is basically the cleaner version of this noisy spectrogram, assuming it does the cleaning very well, right? So this is a noisy spectrogram. Let's say I speak, I am going to school. This is some audio, some utterance, and this audio, let's say it's recorded in clean condition, but let's say we add noise to it and we get this spectrogram. We have clean version of this noise spectrum because we added the noise to it. So output, whatever we get, we'll compare it with the clean version of this output spectrogram, clean version of this spectrogram, so that it's so that we can compute the L2 loss. So basically L2 loss is let's assume mean square error loss, and this mean square error loss should be lower if your enhanced audio or enhanced spectrogram is closer to the reference spectrogram, which is clean, right? This is how speech enhancement modules are trained. I mean, there are various versions of it. Let's say people use CNNs. Let's assume people can use attention, and some people have used TDNN, some people have used normal feed-forward neural network, so on. There are so many papers on this line. That is how people used to train speech enhancement model before. Now let's see another way, which is introduced in this paper, to train speech enhancement module, right? So what we do is, in this paper, what they are doing is, they take the original spectrogram, right? This original spectrogram is a noisy spectrogram, right? And this spectrogram as associated speaker labels. Assume we have some speaker identification data set, and we know who spoke in the list of all the speaker, whose audio is this, right? And this audio, as let's say we add noise to it and create a noisy version of this clean audio. Let's say that is a noisy audio. It goes to speech enhancement, and outputs we get enhanced spectrogram, right? Enhanced spectrogram is basically assuming this noise is removed and we get a clean spectrogram here. Now this spectrogram actually goes to speaker verification model, right? You can ask, like, how do you train the speaker verification model? Assume this speaker verification model is pre-trained, trained on some audio data, pre-trained and fixed, right? This speaker verification model simply takes some spectrogram as input and outputs probability scores over all the speakers. In this case, they are assuming there are 4 speakers, right? Because the outputs are distribution over 4 speakers, and this is pre-trained. You can ask me, why do you want to pre-train? You could have trained this model along with this model also, right? But what these guys are claiming is to train this model efficiently, you need a strong prior. The strong prior is obtained by training the speech enhancement speaker verification model beforehand, or speaker identification model beforehand. So if you train that speaker verification model, this gives a strong prior over training. Strong prior in the sense it gives sort of very good features which can be useful for training this model, because the output should be good. Otherwise, if you want to train from scratch, the outputs will not be right, so that this model will also get affected. So usually what these guys are doing is, in current situation, they are pre-training this model using some voxel data, whatever the speaker identification data, and they are freezing it. This is freezed during training of this whole thing. So what happens is, what happens in the whole the sequence is like this: take the spectrogram, which can be noisy, feed it to speech enhancement model. It's some sort of convolutional neural network, gives you some mask, and that mask will be added on pointwise multiplied to the noisy spectrogram, and you get clean version of it. You just feed forward through it, you get some output score. Now this score, this is the probability distribution over all the speakers, and the ground truth speakers, you compute the cross entropy loss. right? CE loss. Now this CE loss is a loss which can be propagated to this speech enhancement model. Assume we are not going to update this model. It's a freeze model. We are only going to update the enhancement module so that we train the enhancement model. If you train this model in this way, what these guys claim is your speaker verification accuracy will improve, right? That's what they are claiming. This is the whole idea. Let's see some details in the architecture. So the first architecture, first model which I showed you, it's called masking network, which is nothing but the speech enhancement model, and this is our normal speaker verification model, right? As I said, this is pre-trained and fixed. It's not trained. It's pre-trained using some data, and it's frozen, right? And it has convolution layers, fully connected layer, and it has also has a global max pooling layer, all those things. And assume it's some sort of convolution neural network, sort of like a VGGNet or ResNet, whatever. And we have output, which is going to be the probability scores over all the speakers, and we compute the cross entropy loss using the ground truth speaker ID and the predicted scores, right? So that is the thing, and the fun part is here. The fun part is called masking network. So what is this masking network? The masking network takes a noisy spectrogram, and the spectrogram is of size 257 cross 298. So this 298 is basically a total number of frames in the spectrogram. Basically there are 298 because they are considering 3 seconds of audio data, and with a 10 millisecond shift plus 25 millisecond bin width or the window, and that's how they get 298. And 257 is basically the number of frequency bins, right? Assume you are computing FFT of 512, and since we don't use FFT of 512, we have to divide by 2 because the Fourier transform is even when you compute it. So that's why we take 257 of them, first 257 of them. So we get this matrix, right? This is our noisy spectrogram, and this spectrogram will be going to go to some CNN. Here they are mentioning there are 11 dilated convolution layers, and you can see the paper for the details of number of filters used here and all. Assume there is some CNN. The CNN is constructed such a way that the output at the last 11th layer is going to be this ratio mask, right? The size of this ratio mask and size of our input is exactly same, right? 257 cross 298. This is also 257 cross 298. Why do you want this to be same is because you have to do something called pointwise multiplication of this and this, which is what is shown here. This is the pointwise multiplication, right? PM, let's call it. So this pointwise multiplication, basically what happens is, let's say you have a matrix 1, 2, 3, 4, and you have another matrix 0, 1, 0, 1. Pointwise multiplication is you multiply this by this, you multiply this by this, this by this, and this by this. That's all. That's a pointwise multiplication. When you do that, what happens is the high frequency noise, basically the noise content or noise frequency content, or each point is from bin and its corresponding frequency, and that will be suppressed if the mask has 0 approximately 0. So that's how you are going to suppress all the noise component and keep only the speaker related component, and that speaker related component can be passed through the speaker identification model and get our probability score over all the speakers, right? Probability distribution P, or all the speakers P speak, let's say. This is how the algorithm works. When you compute it, when you get probability distribution over all speaker, you know the ground truth vector, like 0, 0, 0, 1, what I showed you in the previous slide, and you can compute CE loss easily, and that CE loss is going to update this speech enhancement algorithm, right? Or speech enhancement CNN, right? This is how the algorithm works, and this algorithm is called VoiceID Loss algorithm, right? This is as simple as that, right? I hope you guys understood. Let's dig into some of the details. For this, they are using VoxLab 1 dataset. It has, I think, 1251 speakers, and they are also using the same dev data for training and test data for validating the model. And they don't just use VoxLab data because it is a clean data. I know it's not a clean data because it's coming from YouTube. Assume it's a clean data. We actually want to add noise to the data and see how our model is performing on speaker verification. For that, they are using Muson data. For this data is basically it has a noise, babble noise. So, it has different types of noise, different types of music and all. This is some sort of data people use for noise augmentation in speech at least. So this data, they took this data and they generated corrupted version of VoxLab development data, which is the training data called d power n. So let's call it as d power n is a noisy version of our training data. Noisy version, and you have t power n, which is a noisy version of our test data, right? And sorry, this is supposed to be t power n. For the development, they again, how do they do it is they corrupt the clean data, which is the VoxLab1 actual data, by different different signal to noise ratio, like varying from 0 to 20 linear scale, right? That's how they correct. That's how they get the noisy generated data, and also the test data is done in the same way with 4 different types of noises. 4 different types of SNR: 0, 5, 10, 15, 20, and as I said, they have 1,211 speakers for training, and this is the number of utterances in the data, and basically. This is just some sort of statistics that is supposed to be capital power n, because we are using t power n. Some sort of statistics of how the data is and how many utterances are there for each network. And coming to the second understanding, which is what is the speaker verification model, which we said the pre-trained model, right? So the pre-trained model is basically has one dimension convolution, and the convolution is done in the frequency axis, not on the time axis. So this is t axis, this is f axis, and this is basically they consist of 4 1DCN layer, and these are the filter weights and so on, and they have 2 fully connected layer, and those are the numbers, and the input is going to be 257 dimension frequency. This is going to be 298 cross 257 dimensional matrix as an input to the model, based on this is the window size and this is a shift. Coming to the experiments, so as I said, they use VoxLab data for training and testing, and they compute EER and DCF, detection cost function, equal error rate, for evaluating the model, and for the baseline they use denoising autoencoder based speech enhancement model, which is sort of the same model. I think the algorithm was again the same model was developed by the same team, I mean GIMS class students, and that model has this architecture is a TDNN plus L2 loss for training, and you can refer to this paper. This is the paper which explains that. And coming to the results, I will explain only one result. They have conducted some other experiments, like how the spectrum looks and all. You can go and refer to that in the paper. This is how the algorithm results are. So assume you have different types of noises. Noise is some sort of noise, and this is some music, background music, babble noise is there, and reverberation, right? And they also consider on the test data the SNRs, right? As I said, these are the different SNR, varying the SNR. And they have 2 experiments. One is using only the original data and using the noise augmented data. And for the proposed approach, if you look at the results, the EER is consistently better compared to the DAE. DAE is basically the noise, denoising autoencoder. And you can see even the DCF is better, and in the EER is better in the case of, in this case, for all the cases, all different types of noise, all different types of SNR, this model is performing very well. Only one case is this one, where the DCF is little bit lower compared to the DAE. Same thing happens same thing happens with noise augmentation also. In fact, noise augmentation actually gets you better results. You can see here, for example, this number 8.1 comes down to 7.83 if you do noise augmentation. So this is the result. You can see these numbers in the paper. And that's all for this tutorial. Thank you so much for watching this tutorial. If you are not subscribed to my channel, please subscribe. If you like this tutorial, please give a thumbs up, and thank you.